Hi guys, today we shall be looking at organic chemistry. Organic chemistry to say is the study of living things. And when we say living things, what do we mean? We mean plants and animals. Because plants and animals contains organ, has its sounds. So plants contains the following organs. We have the roots, we have leaf, and we have stem. These are the three major organs of plants. Then for animals, we have kidney, we have skin, we have liver, etc. Right. But if we define organic chemistry as the study of living things, it will seem to be like the definition of biology. And so organic chemistry definition has been modified to be the end product of living things when they undergo combustion. And what's this end product? The end product of all living things on combustion is carbon and its compounds. And we'll say compounds of carbon. What do we mean? We mean compounds that are formed when carbon reacts with other elements. For instance, when carbon reacts with oxygen here, we have CH4, which is methane. When carbon reacts with oxygen, we have carbon monoxide, or we have carbon 4 oxide. Then when carbon reacts with chlorine, we have tetrachloromethane, CCl4. Then carbon can also react with a number of elements. As it is here, it's reacting with sodium as well as with oxygen, 3 atoms of oxygen to form sodium tricarbonate. These are all compounds of carbon. But note, not all the compounds of carbon are organic compounds. So what are the exceptions? We have oxides of carbon has an exception for organic compound, oxides of carbon. And what do we mean by oxide of carbon? It means carbon reacting with oxygen to form a compound. It means this is not an organic compound because it's an oxide of carbon. So e.g. here we have CO, which is carbon monoxide, and CO2, which is carbon dioxide. Then another exception we have is carbonates. That is compounds that are characterized by the radical CO2 CO3 2 minus. Example, we have sodium Na2CO3, sodium tricarbonate. If the CO3 is not reacting with sodium, we can have another example like calcium. It can also react with calcium. So we can have calcium tricarbonate, which is limestone, etc. Apart from that, calcium carbides or carbides generally are exceptions for organic compounds. For instance, we have calcium carbide. In a nutshell, we can then modify the definition of organic chemistry as the study of carbon and its compounds, with the exception of oxides of carbon, carbonates, and carbides. Now, apart from the fact that organic chemistry definition has been modified to be the end product of living things on combustion, another reason we cannot define organic chemistry as a study of living things is because that fact has been defaulted by a German chemist named Friedrich Hohler. He was able to synthesize tolurea from NH2, right, from an inorganic compound, ammonium thiocyanate, right. This is inorganic in nature and it is called ammonium thiocyanate, which means that not all organic compounds are formed from living things. Some can be synthesized from inorganic compounds. And so we cannot define organic chemistry as the study of living things alone, because it can also involve the study of inorganic compounds, since they can be modified or organic compounds can be synthesized from them, right? Hydrocarbons. Note that plants and animals contains a number of organic compounds. So taking a species of plants, for instance, a mango, into consideration, let's assume mango contains about 6 organic compounds. And looking at each species of different plants, for every geographical area, we'll have millions of organic compounds. So it seems very impossible to study all the organic compounds around the world. Hence, we can, as a class, limit our study to the simplest form of organic compound, which is hydrocarbon. So, hydrocarbon is defined as the study of hydrogen and carbon atoms only. Note that the chief source of hydrocarbon is crude oil or petroleum. And so we can have impurities in hydrocarbons. We can have impurities like fluorine. We can have impurities like chlorine. We can have impurities like oxygen. We can have impurities like sulfur and so on. So what does impurity does to a pure compound? It either affects the melting point, the boiling point. Sometimes it might even increase the number of isomer of such compound. These impurities sometimes can be envisioned to be functional groups. And what does functional group does to a pure compound? It affects the characteristics of such compound. So it either affects the melting point, the boiling point, the malleability, the number of isomer, and so on. Right. We'll get there soon. So let's look at classification of hydrocarbons. Hydrocarbons can be classified into three majorly. We have aliphatic hydrocarbon, we have aromatic hydrocarbon, and we have alicyclic hydrocarbon. So focusing on aliphatic hydrocarbon is subdivided into two. We have one saturated hydrocarbons and we have unsaturated. For aromatic compounds, we have basically benzenes and its derivatives. Then under acyclic hydrocarbon is subdivided into two. We have cyclic hydrocarbon and we have acyclic or acyclic hydrocarbon, whichever way you call it. Now, saturated hydrocarbons. Why are they called saturated hydrocarbons? They are called saturated hydrocarbons because they have only one bond between their molecules. So for saturated hydrocarbons, why is this called saturated hydrocarbon? It is majorly because the parent name, which is alkane, under it has only one bond between its molecule. Now, what do we mean by having one bond between its molecules? For instance, example of alkane is ethane, right? Ethane is given as C2H6. So it has two carbon atoms and six hydrogen atoms. Six hydrogen atoms. So observe that the bond between the two carbon atoms present is just a single bond. Hence, it is a saturated hydrocarbon. It's a saturated hydrocarbon. You get it? So once the bond is just single between the carbon to carbon existing in the molecule, it is saturated. Now, for unsaturated hydrocarbons, such as alkene, alkynes, alkenes and alkynes. So alkenes are characterized by double bond, alkynes are characterized by triple bond. Once the number of bonds between the carbons in the compound is more than one, such compound is said to be unsaturated. For instance,
ethane is a member of an alkene, just member here, right? And it is given as C2H4. C2H4. So we can have C, hydrogen, and we have a double bond here. So this makes it unsaturated, an unsaturated hydrocarbon, right? So let's look at this example. Provided we have a compound like butene, butene is still, look at the ending name in. This is also an in. Hence, is a member, is a homologue of the parent alkene. So we can have C, 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 right? And let's say the double bond lies here. So it means that we'll have two hydrogen here. We have one. We'll be teaching how to place the hydrogen atom in our next video. So we have H, 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 and H, right? This is butene. Butene is characterized by C4H8, right? So if you have C4H8, would it be an unsaturated hydrocarbon or a saturated one? It will be a saturated one. Why? Because you have double bond taking the priority. Once double bond is there, the single bond does not take priority over the double bond. Hence, this is an unsaturated hydrocarbon. It is unsaturated. Does that make sense? For alkynes, let's take propine into consideration. So we have C3H4. So I have carbon to carbon, carbon to carbon. So let's put the triple bond here. Then we'll have CHH, right? 3 hydrogen atoms surrounding this carbon, and no hydrogen atom is surrounding this carbon. Why? You might be asking yourself why I have not been putting hydrogen on certain carbon atoms. It is just because carbon must be surrounded by 4 bonds in total. So if you look at this carbon, it's surrounded by 4 bonds, which are the hydrogen bond, including this bond connected to the carbon, right? This carbon also is surrounded by 4 bonds, and the last one too is surrounded by 4 bonds. So it will be very erroneous to add one more bond here, creating an hydrogen atom, right? So in that sense, it's also go in line with the fact that hydrogen is number 6 on the periodic table, and its electron is distributed as 2,4, right? 2 as the inner shell and 4 as the outermost shell, which is the valence shell. Note that only the valence shell undergo bonding, and hence we have only 4 bonds surrounding carbon in its outermost shell. In a nutshell, we have 3 bonds between carbon and carbon here, and hence it is said to be unsaturated hydrocarbon. Right. We can have another example here, which is botuine. Botuine. So botuine is given as C to carbon, carbon, right? So the ine is telling you the position of the triple bond, right? So we have it must be at carbon 2, at carbon 2. So if I want to number it, I'll have 1, 2, 3, and 4. So the triple bond is between carbon 2 and carbon 3, right? So, but carbon 2 takes the priority. I'll be teaching that in my next video. Endeavor to go through it. So I have carbon atoms surrounding this hydrogen, 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 and then I have hydrogen. I'm being careful of where I am placing my hydrogen atom because of the triple bond, right? So because of this triple bond, it is an unsaturated hydrocarbon, right? Now, how then can we distinguish between a saturated compound and unsaturated compound? Or how can we distinguish between alkane and alkyne, or alkene and alkyne, right?
so to distinguish between saturated and unsaturated hydrocarbon. So when we say saturated hydrocarbon, we mean alkanes, right? And when we say unsaturated hydrocarbon, we're talking about alkenes and alkynes. Okay, to differentiate between them, we have two possible reagents that can be used to distinguish them. So we have number one, the bromine water test. So the bromine water test, when bromine is added to alkanes, there won't be any effect, right? Don't forget that bromine has a particular color. It has a reddish brown color, right? So it means that when it is added to alkanes, it won't have any effect. The color will remain the same. But when added to alkenes and alkynes, the color will turn colorless. So it decolorizes the color of the bromine water. Right here too, it decolorizes it. Right, it means that we'll have it to be colorless. All right, the same thing applicable to potassium permanganate. Potassium permanganate is pinkish in color, and so when added to an alkane, probably a methane, ethane, propane, butane, or any other members of alkane, it has no effect. Sorry, this should be no effect. No effect, right? Here too, it will be no effect. No effect. Then, on addition of potassium permanganate, KMNO4, to an alkene, there are two possible outcomes. It's either the color turns from pink to colorless, or it forms a brown color. Right? The brown coloration is a result of the presence of the formation of MnO2, manganese 4 oxide. When added to an alkyne, it becomes colorless. So what do we mean by cyclic and acyclic? So when you say an hydrocarbon is cyclic, it means that the shape formed by such hydrocarbon can be inscribed in a circle. For instance, we have a cyclohexane. Cyclohexane is in this form, right? So I can have something like this. So this is a cyclohexane. The idea behind cyclic compounds is that they can be inscribed in a circle. So if I take an hexagon into consideration, I'm going to have a cyclohexane, right? So if I make it double bond here, for instance, I'm going to have cyclohexene. I'm very careful about the position of the double bond, right? So I can have cyclohex 1, 4 diene, for instance. So if I have something like this, right, I can have 1 and this here. So I have 1, 2, 3, 4, 5, and 6, right? So the in has take the lowest position. So if I go this way, it takes the lowest position here. So it means that the name of the compound here will be cyclohexane 1, 4 diene, because I have two ins there, right? So this is how to think of cyclic compounds. Sometimes a square can be given to you to name as a cyclic compound. So what you should just know that each edge of this box represents a carbon atom. Each edge represents a carbon atom, right? It means that I have a both. 4 carbon atom means a both. So it means I would say that I have a cyclobothane. A cyclobothane. So if I have a double bond there, I'll have cycloboth 1 in, something like that. All right. So that is that on the cyclo and the cyclic hydrocarbon. So for acyclic hydrocarbon, okay, before I move to acyclic hydrocarbon, I should mention that we can classify the benzenes as one of the cyclic hydrocarbons, right? Apart from the anes and the ines, because cyclic hydrocarbon is benzene, right? So it can also be inscribed in a circle. So it's a cyclic hydrocarbon, right? Okay. Then we have acyclic. Acyclic hydrocarbon means straight and branch chains, like the aliphatic hydrocarbons, right? So we have seen, right? So we have hydrogen, like both A is an acyclic hydrocarbon because it's not in form of a circle, right? So this acyclic hydrocarbon. Then I can have some other acyclic hydrocarbon if I change this to from this butane, right? So I can change it from butane to probably 2-methyl propane. So I have H here, hydrogen, hydrogen. Okay, so I have an isobutane here, or 2-methyl, 2-methyl propane. This 2-methyl propane. So for alkenes, alkynes, and alkanes, they are usually acyclic hydrocarbons. So what do we mean by benzene and its derivatives? This is the structure of benzene, right? So I have this as benzene. Okay, note that for each angle of benzene, we have a carbon atom there, but the carbon atom is connected to one hydrogen atom, one hydrogen atom, one hydrogen atom, and that is why benzene is given as C6, because for each edge we also have a carbon atom there. So we have, in total, we have 6 carbon atoms and 6 hydrogen atoms. So the formula for benzene is C6H6. If you have a compound that is a benzene compound but having a functional group connected to it, so in the place of hydrogen here, we now have another functional group connected to it. So we'll have like OH, right? So instead of it to be called benzene, it is called phenol. Phenol. So this is a derivative of benzene. And where is the word phenol coming from? When benzene loses one hydrogen atom, which is supposed to be here, it becomes C5, C6, right? H5. This is an aryl compound. So it is called instead, not called benzene, but called phenyl. Phenyl. So having phenyl and an hydroxyl group all, right? The two can be combined to form phenol, and that is that on hydrocarbons.